Hello, everyone. We're going to go ahead and go over section 3.7, which is our final section in chapter 3. It is on polynomial and rational inequalities. So we've learned about polynomial functions at this point. We've learned about rational functions at this point. Now we're going to look into how would you solve an inequality that contained one of these. So we want to recall inequalities that contain the symbols less than, greater than, less than or equal to, greater than or equal to, which all of these definitions here, respectively. That's how we would read them. So this one right here is less than, greater than, less than or equal to, greater than or equal to. Those would be inequalities. So any inequality that you have would look like an equation, but instead of having an equal sign, you would have one of these inequalities. So that would be an inequality that you would have to solve for. So we can solve basic inequalities by solving for the variable in an expression. You have something like x plus 2 is greater than 0. You would just solve for x by subtracting 2 from both sides. You would get x greater than 2 or negative 2. So in that case, for something like that, you would just solve for the variable. But when you have things like polynomials and rational functions, they are not as straightforward because they have multiple terms for your variable. You're going to have multiple x's, any other term that they would have, although x is the most common one that you will see. But you'll see that they have multiple variables in that case. So it's harder in that sense because that's not as straightforward. But we're going to learn what we use so far, and we're going to apply the inequalities to polynomial and rational functions. So we have some basic examples here for inequalities, just to remember what they're about. So if you have like one puppy is less than 3 puppies because 1 is less than 3. That's how we would use inequality. So 1 puppy less than 3 puppies. And then maybe for greater than or equal to, maybe your parents, they say, hey, we'll give you some money if you get a B or greater on your next exam. So something like that. So we've got, you could potentially earn some money if you get a B or better. So better than or equal to, or greater than or equal to a B on your next test. So these are just some kind of like silly little, normal inequalities that, you may encounter. Just give a little bit of application. But all right, so now we're going to go into polynomial inequalities to start off with. So definitely not as easy as the 1 versus 3 puppies that we have here. But an important consequence of polynomial functions is that the values of a polynomial does not change sign between the successive zeros. So we learned about what a zero of a polynomial was. We said that that is the x-intercept. It's a solution. It's where your polynomial equals 0, the value of as 0. So remember, we're using the same word there. So if you find zeros, those are values of x's where your polynomial actually equals 0. So that's why I call them that. But so we know how to find zeros of polynomials, and something that is a benefit of polynomials is that your polynomial will either stay positive or stay negative between every 0. So graphically, this means that really you're looking between the x-intercepts. The graph of your polynomial would be entirely above or below the x-intercept, or the x-axis, sorry. So we said that since zeros were x-intercepts and your graph is crossing through the x-axis, we're saying that your graph is either above or below the x-axis at that certain time. So if we look at our picture here, we have this polynomial. It's p of x is equal to 4 times x minus 2 times x plus 1 times x minus 0.5 times x plus 2. So we have our graph here. This is our polynomial, and we see it's crossing 1, 2, 3, 4 times across the x-axis there, and there are 4 zeros. So this makes sense. And we see that between every 0, the graph is entirely above or entirely below the axis. And this is a fact, and we can use that fact solving for inequalities, because it means that if we know that some number over here is positive, we don't need to check every single number. We know that the graph would then be positive for values over here of x. Same thing, maybe values of x between these two numbers here, we would see that our entire graph was negative. So we don't need to check the value of our graph for every single x value in between these two zeros. As long as we check one and it says it's negative, That means that our entire graph would be negative between those x values on that interval. So we have intervals as our answers here. So we see that when your graph is above the x-axis, it is greater than 0. So p of x is greater than 0 in the kind of light yellow kind of shaded regions in here. And p of x would be less than 0 in the darker kind of orange areas there as well, because it's below the x-axis. So if you want to know when a polynomial is greater than or equal to or less than or equal to or just greater than or less than 0, which is the most common value you'll see, you want to know when is it going to be above or below the x-axis. That's really what you're asking for. So this property is going to allow us to solve polynomial inequalities by finding the zeros of your polynomial and then using test points in between those zeros to determine the specific intervals that satisfy your inequality. So you'll solve for polynomial inequalities by finding the zeros, doing some of the things that we're going to see in an example, and using test points to test each interval and then deciding which interval satisfies the inequality in the end. So that's how we'll solve inequalities, but here are our actual guidelines, our steps. So guidelines for solving polynomial inequalities. We have step 1, move all of your terms to one side. Rewrite the inequalities so that all non-zero terms appear on one side of the inequality symbol. So you want to bring all of your terms over to one side, and you would do this by adding or subtracting, not by dividing or multiplying. So just remember that. When it comes to polynomial inequalities, it's adding or subtracting to bring everything to one side. Then step 2, you would factor the polynomial. So given that all of your terms are all on one side, you've got one polynomial, greater than, less than 0, maybe some equal to's in there, but then you want to factor your polynomial. So you'll factor your polynomial into its irreducible factors. So as much as you can reduce them without any imaginary numbers. We're not in 3.5, but we will not be using that if it's not about section 3.5. So factor the polynomial into its irreducible factors and find the real zeros of the polynomial. So you want to find the zeros, specifically the real zeros. Once again, no i's. We don't have any imaginary numbers anymore at this point. So it's just the real zeros of the polynomial. Step 3, you would find the intervals. So you would list the intervals determined by those real zeros. So the best way to do this is to draw yourself a number line, write down the values of the zeros in the number line, and every interval on the ends and in between would be your possible intervals that you would have to solve your inequality. But possible, you don't know for sure yet. Step 4 would be that you want to make a table or a diagram. You use test values to make a table or diagram of the signs of each factor in your interval. So in the last row of the table, you determine the sign of the polynomial in that interval. So since your polynomial has now been broken up into multiple factors, you would create a table using each one of those factors and each one of the intervals and seeing on which interval is which factor positive or negative. Since your polynomial would be the product of multiple factors, you would be thinking to yourself, okay, this one's negative, and this one's positive. So it would create a positive number because it would be 2 negative numbers times a positive number, which creates a positive number. So you're taking in the combinations of each one of the individual factors and seeing whether or not they're positive or negative, multiplying all of those together to see what your polynomial is going to be, positive or negative. Then step 5, we'll solve. Determine the solutions of your inequality from the last row of the table. Check whether or not your endpoints of these intervals satisfy the inequality. Now, if you've done this right, you've factored in those inequalities and endpoints, and that means parentheses versus brackets as well. You would have factored that in already earlier on, and so step 5 here is just telling you to make sure that they're correct. You want to check to make sure that they are correct. So, all right, here are all the guidelines. Let's go ahead and do an example. So example 1, we're going to solve the inequality 4x cubed plus x squared is less than or equal to 16 plus 64x. So, all right, let's go ahead and go on over to our notes so we can work on this problem. All right, so we have example 1. We are finding 4x cubed plus x squared less than or equal to 16 plus 64x. So we're going to go ahead and solve this. So we said in our very first step that we want to bring all of our terms over to one side. Personally, I like bringing everything to the left side, but you can bring everything to the right side if you'd like. Just remember to read your inequality correctly. It's the only important thing. That's all right. So step one, I'm going to bring all of my terms to the left-hand side, meaning that I'm going to grab these terms and I'm going to bring them over here to the left. So in order to do that, I'll be subtracting 16 from both sides and 64x from both sides. So we see our terms cancel on the right-hand side there. And since they all cancel, that means that effectively we have 0. We got rid of the 16, we got rid of the 64x. So it would just be 0. And then we can write out our new inequality. Scooch, whoa, scooch this down a little bit. Get that keyboard out of there. Oh man. Whew. All right, we'll just rewrite step 1. There we go. Step 1. All right, so we've got step 1 here. We're going to write this out. We want to have our function or polynomial in decreasing exponential order. So we're going to have 4x cubed first plus x squared minus 64x minus 16. And this is less than or equal to 0. So we brought all of our terms over to one side. For me, I brought it to the left-hand side. But remember, you can always bring them all to the right-hand side if you'd like to do that instead. But remember to read the inequality correctly. So that was step 1. We brought everything over to one side. Step 2 is that we want to factor our polynomial. And if we look at our polynomial, this is a polynomial of degree 3. That's the highest degree polynomial. And we haven't exactly gone through any specific ways on how to solve a polynomial of degree 3. So if we were just looking at this, thinking of how to solve this, probably be a little bit lost. But what we're going to do is that we're going to learn what's called factoring by grouping. So we're going to go ahead and write that over to the side. So factoring by grouping. What you do when you have factoring by grouping is that, for example, we're going to take the first 2 terms and the last 2 terms, and we're going to put parentheses around them. So for us, that would be putting parentheses around 4x cubed plus x squared and 64x minus 16. So we're going to go ahead and do that. So we're going to put parentheses around 4x cubed plus x squared. And then we see here that we have a minus sign in front of the 64x and the 16. So we're going to go ahead, we're going to put the minus sign right in front of our group. We essentially, if we were to get rid of the parentheses, we would distribute that minus sign. So that's what would happen. So we can go ahead and do that as well. We kind of, factor the minus out. So we're gonna have minus in between the groups. And that means that we would end up with 64x minus 16. Less than or equal to 0. So for factoring by grouping, we would say step 1 is to put let's go with the first 2 terms in parentheses and the last 2 terms in parentheses. This is that grouping part. So you've grouped them together. And for our problem, this is going to work really nicely. But, for other problems that you have, you may need to kind of move things around a little bit to get the groups just right. And you'll know when you'll see it in a second here. So step 1, typically the best way to go about it, first 2 terms in parentheses and the last 2 terms in parentheses. So you group the first 2 terms and you group the last 2 terms. If you need to factor anything out, like I almost forgot to do there, that should be a plus. If you factor anything else, just remember to, you know, work that in there. But all right. So once you've gone ahead and you grouped up your two groups, essentially, you're going to go ahead and you're going to find the greatest common factor between the two numbers in each of your groups. So if you remember, the greatest common factor is essentially the biggest thing that you can factor out of both terms. So if we have 4x cubed plus x squared, our greatest common factor, or the biggest thing we can take out of both, would be x squared. So our greatest common factor would be x squared. Now we're going to do that with both groups. So we're going to do it with the second group now. We've got 64x plus 16. So we want the biggest number we can take out of both terms, not just any number. You want the biggest number, because you may look at these and think, oh, great, I can factor out 8. But you can also factor out 16, and 16 is bigger than 8. So 16 would be the greatest common factor. It needs to be the biggest thing you can take out of both, not just anything you can think of, or the smallest or anything. It has to be the biggest, or else this probably won't work. So for our greatest common factor, we take out x squared from the first group and 16 from the second group. So that'll be your step 2. So step 2, you factor out the greatest common factor for each group. So first, we found what the greatest common factor was for each one. Now we're actually going to factor it out in our next step here. So this means that we'll be pulling out an x squared from the first group. So we're going to have x squared times whatever's left over. So what we have left over is 4x plus 1. So as our first group, we factored out that greatest common factor. Now we want to do it to the second. So we said the second group's greatest common factor was 16. So we're going to have 16 times whatever was left over in the parentheses. So 16 times 4x is 64x. So we've got 4x. 16 divided by 16 is 1. So plus 1. And this whole thing is still less than or equal to 0. So we've got x squared times 4x plus 1 minus 16 times 4x plus 1. This is less than or equal to 0. So that was step 2. We factored out our greatest common factor in each group. Now our next step here is something that you may have realized already, is that if you have done this right, those two groups that are still written in black should be the same. If they're not the same, then you cannot do factoring by grouping. But as long as they're the same, this will work. So for step 3, assuming that this is correct, for step 3, you would then factor out the remaining common factor, which is the group that we had written in black. So you're going to factor out the remaining common factor, which the remaining common factor is 4x plus 1. You're going to factor that statement out. And since you're going to factor that statement out, really this means that you're going to grab anything that's not that factor and you're going to put it into its own group. So the way that this is written, you're going to see it like, ooh, wrong color, I want a green over here. Into one group. And these would go in the next group. So we would factor this into x squared minus 16. So we took the greatest common factors and the sign that was in the middle there. We took the greatest common factors plus the sign and we put it into its own group. And the other group was the remaining common factor, the 4x plus 1. So we see that they got split up there, but now they're their own groups. So we see that those colors match and everything now, and this is still less than or equal to 0. So that is how you would factor by grouping. Once you factored out that remaining common factor, step 3, you should end up with 2 statements here, or 2 separate polynomials that you can now either remotely, simply kind of simplify further, or you would essentially be done in one of those ways. We said we wanted irreducible factors. We can still reduce x squared minus 16, but if that were an x squared plus 16 instead, that would be irreducible. You couldn't reduce that anymore without having imaginary numbers. So you would be done in that sense. We're not quite done though. We're going to simplify further, but that is how you would do factoring by grouping. So that is a new technique that you can now use for solving polynomials of degree 3. So, all right, now that we've done that, we're going to go ahead, we're going to factor x squared minus 16 further. And we have mentioned this before, but you could use the difference of squares for this statement. So the difference of squares is that if you have something that looks like x squared minus a squared, this would factor into x plus a times x minus a. So in our case, we've got x squared minus 16. So we want to think to ourselves, is 16 the square of any number? Yes, it is. It is the square of 4. So we can use the difference of squares to factor x squared minus 16. This would factor into x plus 4 times x minus 4. And then remember, we still have that last factor there, 4x plus 1. And there we have it. We've got x plus 4 times x minus 4 times 4x plus 1 is less than or equal to 0. So step 2 has been completed. We factored our polynomial. All right, so step 3 now is that we want to figure out the intervals based on the zeros. So knowing the zeros would be helpful. We completely factored everything from step 2, but we didn't quite find the zeros, so we're going to find the zeros. So this means that we would go ahead, we would go ahead and we would grab each one of our factors from before and set them each equal to 0. So we would have x plus 4 equal to 0, x minus 4 is equal to 0, and 4x plus 1 is equal to 0. So you're going to solve each one of those for 0. This would give you, solve each one for x. This would give you x equals negative 4, x equals 4. And we get 4x is equal to negative 1. So x would be equal to negative 1 over 4. So each of those is a 0. So we're going to write that over here. We're going to say zeros are negative 4, negative 1 over 4, and 4. There we go. So those are the zeros. Now we can move on to step 3. We said step 3 was finding the intervals based on the zeros. So from the zeros, what are the intervals going to be? So like I stated before, the best way to kind of do this is to draw yourself a number line. So you can draw a number line here. We can mark down the important points, negative 4, negative 1 over 4, and 4. So we put all those important points on there. Remember, our number line is going from negative infinity to positive infinity. And we want to look at our function. We have less than or equal to 0. This means that our function can be the values of the zero because it's a non-strict inequality. It can be equal to 0. So that means that when you draw your number line and you write out all of your intervals and everything, that these points are included. So we would draw a filled in point at each one of these. And remember that filled in points corresponds to brackets. So we can use brackets on each one of these numbers. So you want to be able to remember that. If this were a strict inequality, if it said less than 0, nothing else, then in that case you would have to draw open circles because it cannot actually be equal to these numbers. But in our case, we have less than or equal to, which means that they get included, they get filled in points and brackets. So let's go ahead and write that. So our function exists everywhere in here. Technically, our function exists everywhere, but the intervals will be based on the intervals that were created by separating the zeros. So it's not quite as domain because we don't necessarily need to know where our function doesn't exist. Our function exists everywhere because it's a polynomial, but we're just separating it from their zeros. So all right, that first interval, we're going to go from -infinity to -4. And we said that -4 got included, so it gets a bracket. Then we got -4 with a bracket to -1/4 with a bracket. Then we've got -1/4 to 4 with a bracket. And 4 with a bracket to infinity. Remember, infinity, -infinity, they always get parentheses. And we're not naming a domain or anything. We're just listing out the intervals. So we just write some commas. And we'll write intervals. So these are all of the intervals that we are going to use when we create our table, which is in the next step that we have here. So step 4 is where, wrong one. Step 4 is where we create the table. This is really going to help us figure out, what values are going to go where. So when you create your table, you're going to have your first column. It's going to say sign of. Let me scoot that over a little bit. It's going to say sign of. And you're probably going to draw a pretty long line underneath that. And this is the first column, so we're going to separate it down like that. So we've got sign of, and across the top, we're going to write the intervals that we found. So we're going to write -infinity to -4. That had a bracket. Then we've got -4 to -1/4. Then we've got -1/4 to +4. Then we've got 4 to infinity. So we filled in our very top row, and now we're going to fill in the rest of the first column as well. So we've got sign of, and you're going to write every factor in the column. So your factors were x plus 4, x minus 4, and 4x plus 1. So you're going to take these and put them in. There we go. So your first one, you're going to have sign of x plus 4. Create a row. Sign of x minus 4. Create a row. And the sign of 4x plus 1. Create a row. Then your bottom row is going to be the polynomial in and of itself. So we have this x plus 4 times x minus 4 times 4x plus 1. This really came from this polynomial that we found right in here. So we're going to go ahead, just for simplicity's sake, we're going to label this p of x. So really the question that we want to know is, when is p of x less than or equal to 0? So that whole statement there, the polynomial, we're going to call that p of x. So back to under a table, and we write p of x. All right, so when you create the table, you fill in the top row and the first column, and everything else you're going to need to calculate. So next thing that we're going to do is that for each interval, we only need one number from the interval. You don't need to have multiple numbers, you only need one. Because remember we said that between every 0, your function stays above or below the x-axis, positive or negative. So you just need one point to use as a test point to see whether or not your function was positive or negative on that interval based on whether or not each individual factor was positive or negative. So that being said, once you get to this point where you've kind of filled in everything from your table and you haven't quite done any calculations yet, you're going to go through and you're going to pick a number in every interval. And you don't need to make it that difficult. Try to make it as easy on yourself as possible. And definitely don't pick any of the endpoints, because if you do, it'll be equal to 0, which isn't positive or negative. It just makes it more confusing. So you want to pick one number that is in the interval and try to make it easy. So for the interval negative infinity to -4, I'm going to go ahead and I'm going to pick -5. It doesn't matter what point you pick as long as it exists in the interval. So I'm going to pick -5. Then for -4 to -1/4, trying to make it easy, I'm going to go ahead, I'm going to pick -1. My test point. Then, flew away from me there. Then from -1/4 to 4, once again, you want to make it easy as possible. You can go ahead, you can pick 0, you can pick 1, whichever one feels better. Personally, I like 0, so I'm going to pick 0. And then the last interval, we need one test point, and 4 to infinity, next best one is probably going to be 5. So these are the test points right there. All right, put those in parentheses. There we go. So you have your test point, and now you're going to use your test point for each individual factor. So starting off with, we're going to go interval by interval in this case. So we're going to have x plus 4, where we're saying the test point is -5. You're going to replace x with your test point. So for us, this would be -5 plus 4. So we're going to write that. We're going to write these in the first column just so we get a feel for what's going on here, and then we're going to stop writing them for each column after that. But so just to get a feel for what's going on, we're replacing the test point with x. So this is really -5 plus 4. And if we, find what's -5 plus 4, it's going to be -1. We don't care about the value. We only care if it's positive or negative. And -1 is a negative number, which means that x plus 4 is negative on the interval -infinity to -4. So now we're going to do this for x minus 4 as well. So we're going to plug in -5 for x minus 4. So it's going to be -5 minus 4. -5 minus 4 is -9. Once again, we don't care about the value. We only care if it's positive or negative, and -9 is negative. So we write another negative sign. Then we have our last one here, 4x plus 1. You're going to plug in -5 for x. So this will be 4 times -5 plus 1. 4 times -5 would be -20, plus 1 would be -19, which, once again, don't care about the value, only care if it's positive or negative. -19 is negative, so we're going to write a minus or a negative sign in the box there. So we found each one of the factors. The last row is the polynomial itself. So you don't need to use the actual values that you found when you kind of calculated whether or not each factor was positive or negative. You just need to use the fact that it's negative or positive. So really what we have here for a polynomial is that we've got a negative number times a negative number times a negative number. And we know that a negative number times a negative number equals a positive number. But then a positive number times a negative number would be a negative number. So if you multiply three negative numbers together, the answer has to be negative. That means that our polynomial is negative on the interval. So we see that we took one interval and we took each individual factor of the polynomial. We found whether or not it was positive or negative. And then once we found all the factors, we would kind of theoretically multiply all of those numbers together to see whether or not it would be positive or negative. In our case, it ended up all being negative. So we see that's a little different on the next interval. But that is the key of what we're doing here. So we're going to use this thought process to fill in the rest of the table. So for example, we're not going to write the little calculations anymore. So in our next column, we're using the test point -1. So we're checking if -1 would create negative or positive numbers for each one of our factors. So starting with the first one here, let's just highlight the box to show this is the one we're doing. So we're going to have -1 plus 4, that'd be +3. So that's a positive number. Then on our next box, we've got -1 minus 4. -1 minus 4 would be -5. Don't care about the value, just care that it's negative. So it would be negative, that factor would be negative on the interval. Then our next one here, we're plugging in -1. 4 times -1 would be -4, plus 1 would be -3. Don't care about the value, just whether or not it's positive or negative. So for P of X here, in our bottom row, we've got two negative numbers times a positive number. Now, two negative numbers create a positive number, times another positive number would be a positive number. So P of X would be positive on that interval. All right, moving on to our next column here, our next interval, we're using the test point 0. So first box here, we've got 0 plus 4, that's +4, that's positive, so we put a plus sign. Next one, we've got 0 minus 4. 0 minus 4 is a negative number, so we'll put in a negative sign there. Then we have plugging in 0 to 4x plus 1. 4 times 0 is 0, plus 1 is 1. So that would be positive on that interval. So then, looking at P of X, where we have two positive numbers times a negative number, positive times a negative number would create a negative number, and then a negative number times a positive number would still be a negative number. So our polynomial is negative on that interval. All right, now we've got the last one. The last interval, we're using the test point 5. So first factor, we'll have 5 plus 4, that's a +9. So our factor is positive on that interval. Then we've got 5 minus 4, which is a +1, so it's positive on that interval. Then in this interval here, we've got 5 times 4, which is 20, plus 1 is +21. So our function is positive, or our factor is positive on that interval. Then lastly, we've got P of X. We've got a positive times a positive times a positive. If all the numbers are positive, your function is positive. So we've got our final kind of total here at the bottom. So we're saying our polynomial P of X is negative on the intervals -infinity to -4 and -1/4 to +4. And then our polynomial is greater than 0, or it's positive on the intervals -4 to -1/4 and 4 to infinity. So we're just going to make those statements really fast. We're going to say, from these two here, P of X is less than 0, or in this case, it's really less than or equal to, since we've included the values. Then we say over here that p of x is greater than or equal to 0 for those two intervals there. So we've gotten this far. We want to remember what was the inequality from the beginning. So we go back up here. And this was the one we wanted to find. P of x less than or equal to 0. So come back down. And we wanted when p of x was less than or equal to 0. So our answers would be these intervals. So we'll write out our answer. Would be the interval from -infinity to -4 with a bracket. And since there's two intervals, you're going to write a union. So you have a union, -1/4 to +4. And that is our final answer there. Then we said that in that last step, we just want to check and make sure that our endpoints are right, basically saying that we want to make sure and check that, we have parentheses and brackets in the right places. So we remember we said that we wanted p of x less than or equal to 0, so we can include the values of the zeros, which we said were -4, -1/4, and +4. So we look back at our intervals, and yes, we drew square brackets on all the values of the 0 and parentheses on the infinities. So we did do that correctly. And there's our final answer. The intervals -infinity to -4, union -1/4 to 4. All right, so these problems can definitely be a little long if we look at them, and they could definitely be a little bit complicated. So it's definitely very important to know the steps on solving something like a polynomial inequality and being able to do them correctly in the end so you can correctly solve for your inequality. So, all right, that wrapped up example 1. Let's go ahead and go back on over to our notes so we can move on. All right, so that was example 1. Moving on, now we have rational inequalities. So we're still doing the inequalities, except now instead of polynomials, we're going to have rational functions. So rational functions are not quite as nice as polynomial functions. They do not necessarily remain continuous like polynomial functions. So their intervals in which your rational function doesn't change sign is determined by now two things: the vertical asymptotes and the zeros, or the x-intercepts. So previously with polynomial inequalities, it was just the zeros or just the x-intercepts. But now we have vertical asymptotes and x-intercepts. So two things are going to determine whether or not your function is positive or negative, above or below the x-axis. So we're going to say that vertical asymptotes and x-intercepts are now going to be called cut points. So instead of just saying zeros, you'll say cut points, and cut points include zeros and vertical asymptotes. So if we look at our function here, we say r of x is equal to x minus 2 divided by x minus 4 times x plus 3. So here's our rational function. So we see that there is a 0 when x is 2. So our function crosses the x-axis when x is equal to 2. But then we have vertical asymptotes at 4 and -3. So we see here, this is -3, this little dot right here. And so our function is either going to positive or negative infinity for this one value of x. Then it also has a vertical asymptote at 4, which is this point right here. And we see the same thing. One side is going to negative infinity, the other side is going to positive infinity. So now, instead of just zeros determining whether or not your polynomial is positive or negative, we now have rational functions, and it's going to be vertical asymptotes and x-intercepts. So your cut points, which is a combination of the two, of r of x, your rational function, are the values of x at which the numerator and or the denominator are equal to 0. So the zeros are the numerator, and setting values of x where your denominator is equal to 0 as the vertical asymptote. So it's the same process, but with each the numerator and the denominator to find separate things. So taking the numerator and setting it equal to 0 and solving for x finds the zeros. Taking your denominator and setting it equal to 0 and solving for x finds the vertical asymptotes. So it is important to remember that, because if you do get them kind of switched up, your answers will probably be very different, and they might, tend to be wrong. And just with everything else we've learned in chapter 3, it's important to know the difference between the two as well. So, all right. We can use test points once again to successfully, between all of the cut points, to successfully determine the intervals that would satisfy your inequality. So the process or the guidelines for solving a rational inequality is very similar to the same process as solving a polynomial inequality. Really, the only difference is that instead of finding zeros, you're finding cut points. But other than that, it's about the same. So, all right, we're going to go ahead and move on here. Just one last quick look at the graph here. We do see that once again, when it's above the x-axis, that's when your irrational function is greater than 0 or positive. And when it's below the x-axis, that's when we see the rational function is less than 0 or negative. So, all right. Here are our guidelines for rational inequalities. Step 1 is move all of your terms to one side, the same as last time. So you rewrite the inequality so that all of your non-zero terms appear on one side of the inequality symbol. Bring all your quotients to a common denominator if they don't already. So one thing that can happen is when you move all your terms to one side, remember when you move your terms to one side or the other, you are adding or subtracting. You don't want to be dividing or multiplying or anything like that. It's okay if you do, if you end up multiplying or dividing, if you deem it necessary with a rational inequality, you just have to remember that you're not left over with 0, you're left over with 1. So if you decide to do any multiplying or dividing to get rid of any terms or anything like that, whatever's left over is 1, it's not 0. When you add or subtract terms to one side to move them over to one side, you're left with nothing. You're left with 0. But if you multiply or divide, you're left with 1, not 0. So it's just important to remember that. You may see it a couple times on your homework. But all right, so you move all your terms to one side. You do this by adding or subtracting terms, bringing everything over to one side if it's not already. If they're not in a common denominator, you have to bring them to a common denominator. So if you have two rational functions, one plus or minus the other one, you have to bring them together. You have to combine them. Then step 2, factor the numerator and the denominator. Factor the polynomial and irreducible factors and find the cut points. So that means factor your numerator and factor your denominator, set them both equal to 0, solve for the cut points, the zeros, and the vertical asymptotes. Step 3, find the intervals. List the intervals determined by those cut points, same as we did before. Step 4, make a table or a diagram, the exact same table or diagram as we made before. We use test values to make sure the table or diagram of the sign of each factor is in each interval. In the last row, you determine the sign of the rational function on that specific interval. Step 5, solve. Determine the solutions of the inequality from the last row of the table. Check whether or not your endpoints of those intervals satisfy the inequality. Now it becomes a little bit more important to pay attention to those endpoints, because your function cannot equal a value that would make your denominator equal to 0. You cannot divide by 0, which means that you will never be allowed to be equal to a vertical asymptote. So that means that any vertical asymptote permanently gets a parentheses, not a bracket. So it's important to really double check that in the end. Make sure that you did it right the first time, then make sure that when you write your answer that you did it right. So your vertical asymptote never gets included, but values of your zeros do. So important to remember that. All right, let's go ahead and do example 2. Now, our example 2, we want to find the domain of f of x, which is equal to the square root of 7 plus x divided by 7 minus x. Now, this is not solve the inequality. It's different. We're finding the domain of this function, but the whole section's on solving inequalities, and what we just learned was solving rational inequalities. So this is going to be a rational inequality, even if it isn't exactly set up as one. So let's go ahead and go on over to our notes so we can go ahead and work on this problem. All right, so here we are with example 2. We said we wanted to find the domain of f of x, where f of x is the square root of 7 plus x divided by 7 minus x. So one thing that's really important to remember is, how do you find the domain of a square root function? So we're going to write here the important thing to remember, domain. Domain of a function that contains a square root will be all the values of x that would keep what's underneath the square root greater than or equal to 0. So as an example, if you have a square root of some expression, you would take that expression and set it greater than or equal to 0 and solve for x. So that's how you would find the domain of a function that has a square root. We said square roots are the only things that mess up domains. So really, what we're asking for here is that we're going to take seven plus x divided by 7 minus x. Wrong. And set it greater than or equal to 0. So this is what we end up getting here when we factor out, or we really figure out like what the question is asking for. Because the question is just asking for domain, and it kind of seems simple enough, but really this is what it's saying. 7 plus x divided by 7 minus x greater than or equal to 0. And we now have to solve for this rational inequality. So we see that the rational inequality problem was kind of buried in a domain question. So this is what we're being asked for when you've asked to be like found a domain of a function, and it's got a square root and a rational function's underneath the square root. Your rational function's got to be greater than or equal to 0. All right, now that we've determined the actual problem that we're working on here, we're going to go ahead and use those guidelines that we saw before. Step 1 was to bring everything over to one side. That's already done. We don't need to do anything. 7 plus x divided by 7 minus x is all on one side, 0's on the other, so we're good. It's already done. We don't need to do anything. So step 1, all terms are already on one side. So we can put a little check mark. Step 1 is already done. We don't need to do anything. So we can move on to step 2. Step 2 was to factor. There's no factoring. It's 7 plus x divided by 7 minus x. That's it. There's nothing else to do with that. You don't want to change either one of those to try to match the other one, because it's probably not going to happen. So that's it. It's already factored. There's no more factoring. But in step 2, you would want to find the cut points. So for step 2, we can say no factoring needed. Put a little check mark on that. But we do want to find cut points. So for finding cut points, remember we want to find the zeros and the vertical asymptote. So to find a 0, take the numerator and set equal to 0. For vertical asymptote, take the denominator and set it equal to 0. So for the 0, we're going to take the numerator, which is 7 plus x. And we set it equal to 0. Solve for x. You subtract 7 from both sides, get x is equal to -7. So that is the 0. Then, for finding a vertical asymptote, you would set your denominator equal to 0 and solve for x. So our denominator was 7 minus x equal to 0. And you can add x to both sides, or you can subtract 7 from both sides and get rid of the negative. But either way, you would get that x is equal to +7. And that's the vertical asymptote. But remember, cut points is just both of them. So your cut points, in this case, are equal to -7 and +7. Where +7 is a vertical asymptote, and -7 is the 0. But your cut points would be both negative and +7. So we found the 2 cut points. Step 3 is remember that you want to find the intervals of your rational function, separated by the cut points. So step 3, we're going to go ahead and draw a number line. So we draw a number line. We said -7 was the 0. +7 was the vertical asymptote. What we want to remember is that your function can equal 0. We said we want to know when the rational function is greater than or equal to 0. It can equal 0. So the value of the 0 can be included. So -7 would get a filled-in point. But vertical asymptotes are never included. So on x equals 7, you would put a big open circle because +7 doesn't get included. Then we know our intervals are going from -infinity to infinity. So this means that our function, exists everywhere in here. And our intervals would be broken up. So -infinity to -7, -7 to 7, and 7 to infinity. So we're going to go ahead and write this out. So our first interval, -infinity to -7. Now -7 is included, has the filled in point, which means we're going to draw a bracket. So -7 gets a bracket because it's 0 and it can be equal to 0. So our next interval would be -7 to 7. So we've got -7 to 7. Whoop. 7, there we go. And like we said before, -7 gets a bracket. But +7 is the vertical asymptote, and our denominator cannot be equal to 0, which means that we can't have x equal to 7. It would make your function not exist. So you put a parentheses on 7. Then our last interval there, 7 to infinity. We're already putting parentheses on 7, and infinity always gets a parentheses. So we've got 3 intervals from step 3. -infinity to -7, including -7. -7 to 7, including -7, not including 7. And 7 to infinity, not including 7. So we see that, one number gets brackets and one gets parentheses. So it's important to remember which one gets which. Make sure to write that correctly. All right. So step 3. Step 4 is remember to create the table. So we're going to go ahead and create the table. All right, so here's our table. We say the sign of each factor, which in our case is just going to be the numerator and the denominator. And then each one of our intervals that we already solved for. Then at the bottom there, we've got r of x. Remember, r of x, we're going to say that's your whole rational function. So we're going to say this all right here is R of X. So what this statement is asking for is when is R of X greater than or equal to 0? So this is what we are going to be solving for. So we come down to our table and we're going to calculate each one of these individual boxes the same way as we did before. We're going to pick a test point in the interval, plug it in for X for each factor, and decide if our function is positive or negative on that interval. So let's go ahead and pick some test points. So we're going to say that negative infinity to -7. Let's go ahead and say -8. As a reminder, you can always pick whatever numbers that you'd like, but I always suggest making them easy. So -7 to 7, 0 was a pretty easy number, so we pick 0. And 7 to infinity, the next easiest number is probably 8. But you can decide if you want it to be 10 or anything like that. Remember, these are the test points. All right. Then you're going to use the test points to plug into each factor and see if it's positive or negative. So we're going to take -8 for the first one. 7 plus -8. 7 plus -8 is going to be -1. So that factor is negative on the first interval. Then using -8 to plug into 7 minus x, that would be 7 minus -8. That's a double negative, so it's really plus. 7 plus 8 is 15. And that's positive. So we've got a negative number times a positive number, which creates a negative number. So we're going to go ahead. We say that our rational function R of X would be negative on that interval. Then our next interval, -7 to 7, our test point is 0. 7 plus 0 is 7, which is positive. 7 minus 0 is 7, which is still positive. And then our function R of X would be a positive number times a positive number, which creates a positive number. So R of X would be positive on that interval as well. Then our last interval, we have the test point 8. So we're going to be plugging in 8 into each factor. So 7 plus 8 is 15, which is positive. And 7 minus 8 is -1, which is negative. So we have one factor that's positive and one that's negative on that one interval, which would make R of X negative. Now, as a note, before we kind of wrap up this example here, is that when you're figuring out whether or not your function R of X is positive or negative kind of in the end, there is an even easier way to kind of tell. Instead of using the thought process of what's a negative number times a positive number and a negative times a negative and a positive times a positive, what you can do instead is that you can count the number of negatives in the column, except R of X. I mean, the idea is that you haven't found R of X yet. So to find, and this works for polynomials as well, so this could have worked for the last problem. So to find if R of X or P of X, so polynomial like for the last one that we had, the last example. So to find if your rational function or your polynomial is positive or negative on an interval, you can count the number of negative intervals from the factors. We're just going to say in the column. So the number of negative intervals in the column. So for example, an even number of negatives equals positive. An odd number of negatives equals negative. So you can use this kind of thought process as well. You just count the number of negatives. You don't count the number of positives because they really don't matter. If you have no negatives, that's considered even, so it would be an even number. If you have one negative number, that's an odd number of negatives, your function would be negative on that interval. If you have two negative numbers, that's an even number of negative numbers. That means your polynomial or your rational function is positive on that interval, so on, so on. So you can use this thought process as well if you'd like to do it this way. So it's really just counting the number of negatives, because any number of positives are always going to create a positive number, but throw one negative in there and it's going to change everything. So it really just depends on the number of negatives. So an even number of negatives creates positive numbers. Odd numbers of negatives create negative numbers. So you can remember that as well when you're creating your table. And we see that this happens in our table here. In our first interval, we had one negative number that created a negative result. In our second interval, we had zero negative numbers or negative intervals. So that would be considered even. So you have a interval that is positive for your function. And then once again, the last interval, we had one factor was negative and one is an odd number, which means the result was negative. So once again, you can use that thought process as well if you'd like. Either way, here we go. A rational function, we've determined whether or not it's positive or negative on specific intervals. We want to review what we want. We want to know, when is our rational function greater than or equal to 0? So we'll go to our function here. We want to, remember, determine that this function right here is when r of x is greater than or equal to 0. These two functions are when r of x is less than or equal to 0, because that's when they are negative versus when they're positive. And we wanted to find when r of x was greater than or equal to 0. So our answer would just be this one interval in the center, -7 to 7. Including -7 and not including 7. So that would be our answer. Just as a reminder, just you want to check and make sure that your intervals are right. You have the right, bracket versus parentheses. So we just want to remember that our function can be equal to 0, which means it can equal to 0, but it can never equal the vertical asymptote. So it can be -7 and it can't be 7. Which means that parentheses go with 7, brackets go with -7. Looking at our answer there, that matches. -7 is included and 7 is not. So there we have it. That was our example for, or a second example there for a rational inequality. So, all right, we're going to go and head back over to our notes to go ahead and finish up. All right, so that was example 2. We found the domain of our function was really just a hidden rational inequality there. And that wraps up section 3.7. So in section 3.7, we covered polynomial inequalities, how to solve them, and rational inequalities and how to solve them. So that wrapped up chapter 3 with sections 3.7. So chapter 3 is now finished, and that means we're going to go ahead and move on to chapter 4 after our next exam. So, all right. Good luck studying for your exam, and I'll see you in the next section.